Okay, this is identifying pairs of lines and angles. We've talked about this a little bit, and you've had this in previous courses, but we're going to call two lines parallel lines if they do not intersect and they're on the same plane. So basically, there is going to be notation that's associated with this. If we have two lines that are parallel, these are two lines, we call it L and M. If they're parallel, we actually use this notation, and we'll go into this a little bit more, but we use the notation that if they have the same directional arrows and number of directional arrows, that indicates parallel lines. We have something that's skew lines, and skew basically indicates that that they are not coplanar, and they're two lines that are basically they're not going to intersect. They're neither parallel nor perpendicular. So what I kind of associate with is if you have a box, a three-dimensional figure, this line here and this line here are going to be skew. And the main reason why they're skew is because they're not coplanar, they're not on the same plane, and they're not going to intersect. Two planes do not intersect if they're going to be called parallel planes. So basically, if I were to extend off, have two index cards, and there's no real notation for this, I would just have to tell you that they're parallel planes. And in something like a cube, like in this figure here, parallel planes would be the top and the bottom. Okay, so the symbol with the double dash marks here means parallel, is parallel to, like line L is parallel to line M. The arrows, if they have the same amount of arrows, are used to show that two lines are parallel. We showed that in the previous slide. So if I have two lines, L and M, parallel, you could have doubles, you could have triples, you could have singles, but the ones that match up are the ones that are actually parallel. Like these guys match up, so that means line L and M are parallel. The symbol, we went over this in chapter 2. That means perpendicular. So if I have something that is perpendicular, and this goes off of the one down here, the symbol, the square, is actually used to show perpendicular lines. And this is what a lot of people kind of forget in terms of notation. So if I have line L and I have line M, what shows that are perpendicular is a square intersecting the two lines. That's perpendicular, or forms 90-degree angles. So this measures 90 degrees. Okay, so example 1, which lines, planes in the figure appear to fit the description? So lines parallel to CD and containing point A. Well, lines parallel to CD. Well, we have this guy here is CD's line. So which lines are going to be parallel? If I tell you that this is a cube, so this is a cube, that means that we could have a bunch of different ones that are parallel. AB is going to be parallel to, and HG is going to be parallel to, and EF are going to be parallel to. The ones that are not, AB contains point A. The ones that are not, remember we have to actually contain point A. So these ones all are parallel to, but only AB actually contains the point A. So all these lines here are parallel to each other, actually. But only one is actually containing A. Okay, lines skew to CD's line, so that'd be CD's line here again, skew, and containing point A. Well, again, containing point A, AG and AH are skew. Well, AG is this guy here, and AH is this guy here. Okay. And they both contain point A. So actually, both AG and AH are skew. and you can put the segment as well for the proper notation. What about the next one? So lines perpendicular to CD line and containing point A. So again, with this one, AD appears perpendicular and contains point A. How do we know it's perpendicular? Well, if this is CD's line here, AD's line here, this notation here, because it has the square, indicates a right angle. That means is perpendicular to. And again, you can put line or line segment. What about a plane parallel to plane EFG and containing A? Well, EFG, I always like to kind of color code just to make sure. So EFG's plane is going to be this bottom plane here, EFG, the bottom face, but containing A, and it has to be parallel to. Well, the only one that's actually parallel to is going to be ABC, which is the one that's just above it. So that'd be this guy here. And remember, planes are indicated either with a capital letter, but in this case we don't have a capital letter in the lower right hand, lower left hand corner. Those are all indicating points. So you name it with 3 points. So ABC is going to be parallel to EFG and contains point A. Okay, as before, we have postulates and theorems in this chapter. And the first postulate that we're going to be talking about is the parallel postulate. And it states if there is a line and a point not on a line, then there is exactly one line through the point parallel to the given line. And what this basically says is that if I have point P here, this is point P, there's only one line that I can actually draw through P that is going to be parallel to L. So there exists, or there is exactly one line through P that's parallel to L. And we can name it M if we wanted to. Perpendicular postulate, this is very similar to the parallel postulate, but it states if there is a line and a point not on the line, just in this previous postulate, then there is exactly one line through that point perpendicular to the given line. So if I were to take any line through P, there's only one line that you can draw that actually is going to be perpendicular to L. All the other lines are not going to be perpendicular. And remember, the symbol for perpendicular is the right angle sign here. Okay, so I have this kind of real-world example that is basically an aerial view of a street or a couple blocks in a street. So basically what it states is the given line markings show how the roads are related to one another. So let's name a pair of parallel lines. In this figure, there is only one notational set of parallel lines that are notated. Because they have the double arrows, I can state that MD and FE are parallel lines. And the reason is, remember, naming lines you have to do with 2 points. So MD and FE are the only 2 points that you can name. What about a pair of perpendicular lines? Well, again, I have to look for the right angle, and the only place that I see the right angle is right here. So that's going to be both lines MD, which is this line here, and BM, or BF. So BM or BF is completely correct. They're the same line, so we could also say BM as well. I'm going to put in parentheses because BM and BF are basically the same line. Okay, this one's a little more higher level thinking, and it states, is FE parallel to AC? Well, FE, that requires us to kind of look and see. FE is this guy here, and AC is this guy here. Now this is using one of the postulates that we just showed. But basically, if you see, we have point M here. We already drew a line through point M that's indicated parallel to FE. So what the postulate states is that FE can't be parallel to AC because MD is already parallel. MD contains point M. And by the parallel postulate, there's exactly one line parallel to FE through M. So again, we have FE, we have AC. Since AC's line goes through and contains the point M, that's why the parallel postulate proves this wrong. Okay. In this, you're going to have a lot of different positional angles, and we're going to have something that's called a transversal. And basically what a transversal is, it's a line that intersects two or more coplanar lines at different points. Okay, well, what does that mean? Say I have these two lines. Let's say I have line L and I have line M. If I took a random line that goes through and intersects those two, that's my transversal. It intersects in 2 points. This point here and this point here. And you can label this line as well. So a transversal I'm going to be referring to a bunch throughout this because there are different positions in terms of the angles for transversals. Okay, so angles formed by transversal. You have something that's called corresponding angles. Corresponding means similar position. So similar position angles is what that means. It's just a fancy name for similar position. So here's one example we have. And we're going to say two corresponding if they have corresponding positions or similar positions. Here is one example. You have 2 and 6. That's one example of corresponding angles. I could also have angles 1 and 3 are also corresponding angles. I have angles 4 and 7 could also be corresponding angles. And I have angles 5 and 8 are going to be corresponding angles as well. Notice I put different shapes around them just to indicate which ones are going to be corresponding. So those are corresponding angles, similar position angles. And there are going to be 4 sets when two lines are cut by a transversal. We also have something called alternate interior angles. Alternate meaning on opposite sides, interior meaning between the two lines. So if it's between the two lines, it has to be in the interior of the two lines. So alternate interior, they lie between the two lines and on opposite sides of the transversal. So here's one example, angle 4 and angle 5. I could also have angle 3 and angle 6. I'm just making up these numbers as I go. So angle 4 and angle 5 would be alternate interior. Angle 3 and angle 6 would be alternate interior as well. I have alternate exterior. Now, interior was inside the transversal, or in between the two lines. Exterior is going to lie outside the two lines, but on opposite sides of the transversal. So, here's one example. I have 1 and 8. Another example could be like 2 and 4. Again, I'm making up these numbers, but positionally is what I want you to pay attention to. They're on opposite sides, and they lie outside the two lines. Consecutive. Consecutive is a fancy word for next to. Wow. Consecutive interior angles, meaning they're next to and they're on the interior again. So in between the two transversals, or the two lines. So two angles are consecutive interior angles if they lie between the two lines, but they also have to be on the same side of the transversal. That's why they're consecutive. They're right next to each other. So here's one example, angles 3 and angles 5. Another example would be, let's say, angle 2 and angle 4 again. So those are your consecutive interior angles. Okay, so it says identify all pairs of angles of the given type. So all I did is I just flipped the previous examples that we were associating with on its side. So take a second, you can pause the video and figure out the corresponding alternate interior, alternate exterior, and consecutive interior. So corresponding angles, remember, are similar positioned angles. So similar positioned, what would be the corresponding angle with 1? The similar position would be with 5. Corresponding angle with 2, similar position would be 6. Corresponding angle with 3, similar position would be 7. And last but certainly not least, let's do a star-ish thing, and then we'll do a star-ish thing, so they have the same symbol at least. Okay, so those are your examples. What about alternate interior, alternate exterior, and consecutive? So alternate interior, we have 2 and 7. There's 2, there's 7. They're on opposite sides of the transversal. And then we also have 4, and we have 5 as well. Opposite sides of the transversal. Okay, alternate exterior and consecutive interior. Alternate exterior, remember, on opposite sides of the transversal and lying on the exterior. Okay, consecutive interior. We have 2 and angle 5. And then we have angle 4 and angle 7. So angle 4 and angle 7. They're right next to each other, and they're on the interior.